Hi everyone. This video has been made as a part of assignment 2 of the course Nature Inspired Computing. In this video, we'll be solving vaccine delivery problem using particle swarm optimization. Let us have a look at the problem statement. We are given 9 cities and a 9 cross 9 matrix denoting the distance between each ordered pair of cities. We need to find a path that covers all the cities and is of minimum cost. We are also given that each city has exactly one zone out of yellow, green, white or red as shown in the figure in the right. But we do have some restrictions. The first restriction is that once we enter a yellow zone, we are allowed to visit a green zone from there only via a white zone. The second restriction is that once we enter a red zone, we are allowed to visit a yellow or a green zone from there only via a white zone. Let us have a look on how we can handle these restrictions. We have four types of cities. Once we enter a green or a white zone, then we can travel to any other zone. For these two kind of zones, we do not have any restriction. We have restrictions only once we enter a city which has yellow or red zone. Suppose we are currently at a yellow zone city, we will try to find out which zone city we can visit from this particular yellow zone directly. Let us consider the first case, yellow to green. So can we visit yellow to green directly? We are not allowed to do this because we can only visit yellow to green only if there is a white zone in between. Therefore, we cannot directly travel from yellow to green. Let us consider the second case, which is yellow to white. So can we visit yellow to white directly? Suppose in our path further, we have any color zone here. This dotted path represents that we can have any number of cities in between. We can always use this white zone to satisfy the restriction always for the yellow zone. Hence, once we visit a yellow zone, we can visit any zone irrespective of from which zone we came. Therefore, we can directly travel from yellow to white zone. Let us consider the third case, yellow to red. So can we visit yellow to red directly? If we apply the restriction 2 here, then the restriction 2 says that from the red zone, we can visit a green zone only via a white zone. But we found a white zone here. Hence, we can use the same white zone to satisfy the constraint for this yellow zone while traveling to a green zone. Hence, we can directly travel from yellow to red zone. Let us consider the fourth case, which is yellow to yellow. So can we visit a yellow to yellow directly? If we assume that we found out a way to visit a green zone from a yellow zone only via a white zone. Suppose if we know how to do this, then if we apply this assumption here for this particular yellow zone, then we have a path in which we are visiting a green zone from this yellow zone via a white zone. Hence, we can use this white zone to satisfy the constraint for this yellow zone. Hence, we have a path from this yellow zone to a green zone, and we have a yellow zone, and we have a white zone in between. Hence, we can directly travel from a yellow to yellow zone directly. So, from this yellow zone, except the green zone, we can travel to any other zone. Now, let us look at what happens when we are currently at a red zone. We are not allowed to travel directly to a green or a yellow zone. Now, from this red zone, are we allowed to travel the white zone directly? If we have any zone here in the path from the white zone, then we can use this white zone to satisfy the constraint for the red zone. Hence, we can directly travel from the red zone to the white zone. If we consider this red zone, then are we allowed to travel a red zone to a red zone? But because if we apply the assumption here that from this particular red zone, we will be visiting green and yellow zone only via a white zone, then we can use the same white zone to satisfy the constraint for this red zone. Therefore, from the yellow zone, we cannot travel a green zone directly. From a red zone, we cannot travel a green zone directly. And from a red zone, we cannot travel a yellow zone directly. Therefore, we have translated the restrictions on path to restrictions on immediate next city in the path. We can replace the distance between these zones by infinity in our 9 cross 9 matrix. Let us have a look at the particle swarm optimization technique used. In this technique, we have various particles and each particle denotes a solution to the problem. In our case, a solution is a path which covers all the cities and the objective is to minimize the total cost of the path. Let us assign unique index or ID to each of the cities. Let us have a look at the first idea. Since each particle denotes a path that covers all the cities exactly once, hence a particle can be a permutation of the indices of the city. I have taken an example. It is a particle that denotes a path from the fifth city as the start city and ends at the sixth city. We can have 9 factorial unique particles. Suppose this is some particle A and this is the global best particle or the global best path which has the minimum cost so far. Now in the particle sum optimization, we need to subtract these two vectors. After subtracting these two vectors, we get this quantity. But we do have some problems here. The first problem is that we are subtracting two cities, which doesn't mean anything. The second problem is that the solution space is not continuous. Hence, we cannot apply particle sum optimization directly here. Let us have a look at the second idea. A particle denotes a priority for each city to be taken in the path. We can order the cities based on the priority and make path from the priority order of cities, which will be solution to our problem. That is, each particle is a vector like this. For the ith city, we have xi priority. The variable xi can take value in this continuous range. Suppose we have x1 particle like this and x2 particle like this. Now we can subtract these two particles by element-wise subtraction. This quantity xi3 can lie in this range, which can be clipped to -1 to +1. Hence, we have converted the discrete problem into a continuous problem, and we can use these vectors as our particle in the particle sum optimization. But how we can make a path from a particle? Suppose this is a particle where the value xi denotes the priority for the ith city. Now we need to visit each city exactly once. Suppose we make the path iteratively. That is, this is the current path that we have made. We are starting from the city P0. The next city in the path is P1 and so on. The current last city in the path is Pi, and we need to find what will be the Pi plus 1 city in the path. Now we can look at the distances from the Pi city to all other cities. Let those distances be this vector, where the quantity Cj denotes the distance from the Pith city to the jth city. We can take Cj to be infinity if one of the cities is already in the path, because we cannot visit a city twice. We can take the Cj to be infinity if we have a restriction from the Pith city to the jth city. Now we multiply the vector C with vector x and get this vector. We will choose the next city such that the quantity Ck into xk is minimized. So for whichever city this quantity is minimized, we will take that city as our next city in the path. Therefore, the Pi plus 1th city will be the kth city, which minimizes this quantity. Hence, we can iteratively increase our path till the length of the path is not equal to number of cities. Therefore, from a particle x, which denotes the priority order, we can make a path where each city is visited exactly once. And the objective function will be the consecutive distance between each cities in this path. This idea has been inspired from a paper. But we do have a problem here. We need to fix some start city to make the path iteratively. The particle sum optimization technique was implemented in Python using these parameters. It has been noticed that if we increase the number of particles or the number of iterations, then the global solution found does not change. Therefore, the values have been chosen like this, and the value for W, C1 and C2 have been chosen arbitrarily. The limitation of this technique is that we will find a solution or path which covers all the cities exactly once. And the second limitation is that we need to fix some start city. Let us have a look at the animation of the best path found so far with the iteration number and cost of the path. The figure on the left represents all the 9 cities plotted on a 2D plane. The figure is not drawn to scale, that is, it doesn't represent the actual distance between the cities. The figure on the right represents the cost of global best path. The x-axis represents the number of iterations and the y-axis represents the cost of the path. For this particular PSO run, the start city have been fixed to be this city. Let us begin. We can notice that as the number of iterations increases, the value of the global best path decreases, with the current value being 1657. This is the path that starts from this city and goes to this city, then next to this city, then comes to this city, then goes to this city, then goes to this city, then it goes to this city, and to this city next, and finally it ends at this city. If we move further, then we can notice that the path here is changing and the value of the global best path found so far is also decreasing with the number of iterations. This is the final best path obtained after running the PSO by fixing the start city as this city. We can notice that this path visits each city exactly once and it also satisfies the restrictions. For example, for this yellow city, we are visiting a green city down the path, but we do have a white city in between. And for this red city, we are visiting multiple green cities and a yellow city down the path, but we do have a white city in between. The cost of this path is this. Now let us solve the case A, which is we can visit each city exactly once. But in our current PSO, we have a limitation that we need to fix the start city. Hence, I fixed the start city and ran PSO for by fixing each city as the start city. The figure on the left represents the cost of global best path obtained. The x-axis represents the number of iterations and y-axis represents the cost of the path. After running the PSO 9 times by fixing each city as the start city, the best path obtained, which had the least cost, was this path, which starts at this city, ends at this city, and has the cost this. Now let us solve the case B, in which we must visit each city, but we can also visit some cities more than once. For this, let us define a quantity called repetition vector. This vector is of length of the number of cities in our graph. The quantity AI denotes that we have to visit the ith city exactly AI number of times. Hence, for the case A, as an example, the repetition vector would be this, where AI equal to 1 for all I. Now, let us have a look on how we can use this repetition vector. Suppose we have a graph which has only 3 cities and it has this repetition vector. That is, we need to visit the 0th city exactly 3 number of times, the first city exactly 1 number of time, and the second city exactly 2 number of times. This is our original graph of 2 cities. From this, we make a new graph in which we add redundant cities. For example, for the 0th city, we have added the 0th city 3 number of times, depending upon the repetition vector. In this new graph, we also add edges. We add edges such that for each 0, 1 pair, the cost of the edge would be the original cost which was here. Now, we relabel the cities in this new graph so that each city is assigned a unique ID. Now, in this new graph, we can find a path which visits each city exactly once by using our previous PSO technique which we used to solve the case A. Suppose this is the path that we obtained. These are the indices of the cities in this new graph. Now we can take these indices and translate back to the original cities. The index 0, 1, and 2 correspond to the original city 0. The index 4 and 5 corresponds to the original city 2, and the index 4 and the index 3 corresponds to the city 1. If we translate these indices, then we get this particular path. In this path, we can see that the 0th city is visited exactly thrice. The second city is visited twice, and the first city is visited exactly 1 number of times. Hence, we can convert our original graph into a new graph, and we can run the same PSO which we used to solve the case A, and then translate back the indices. Hence, if we fix a repetition vector, then we make a new graph and we solve identically to case A and translate back. Now, in the new graph, the length of the part would be the summation of these AIs. This is also equal to the total number of cities in the new graph. If we can visit each city at least 1 time and at most 2 times, then each of the AIs can take value 1 and 2. Hence, we can have 2 to the power 9 or 512 repetition vectors, which covers all the ways of visiting any city, either once or twice. And we need to make a new graph for each repetition vector and run PSO on that. From these 512 repetition vectors, I have removed one vector, which is AI equal to 1 for all I, because it is identical to case A. Hence, we have 511 repetition vectors. Now we can run PSO by making the new graph for each repetition vector, and we need to run PSO 9 times by fixing the start city on the graph. Therefore, we have these many number of PSO runs. These many PSO runs run in almost 35 minutes. We can also increase the number of times we visit a particular city, but it would increase the time. Hence, I limited to only at most 2 times. This is the final result that was obtained after running the PSO for all the repetition vectors and by choosing each city as the start city. In this path, we can see that the Ahmedabad is being visited twice, whereas all other cities are being visited only once. And the cost of this path is this. And here, this path also satisfies the restrictions. For example, for this yellow zone, we are visiting green zones, but we do have a white zone in between. For this red zone, we are visiting green and yellow zones, but we have a white zone in between. Hence, we have solved both case A and case B. Thank you.